Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of today's lecture or video is the second law related to the Rankine cycle, and the section is 10.7 of the textbook. So here are the three learning outcomes. At the end of this, you'll know how to define the second law of efficiency of a Rankine cycle. You'll understand how feed water heaters reduce entropy generation, and you'll be able to calculate the exergy destroyed and the second law efficiency for a Rankine cycle, both with and without an open feed water heater. So first I want to review a little bit about exergy and the second law, and that was related to entropy generation. So if you think back to, for example, chapter 8 of the textbook in basic thermodynamics, we would talk about entropy generation anytime you have heat transfer between a finite temperature source. So say I just had a source at T high and it was just dumping heat down to T low of some amount Q. If we wanted to know the entropy being generated, well, the entropy generated is going to be the heat that leaves TH is going to be a reduction because that's heat being removed, but then we're going to add that heat going in to T low. And since we know that T low is less than T high if heat is actually being transferred, that means that this number right over here is actually going to be greater than that number over here. I'm sorry, I should add those two. This number is going to be greater than that, and I'm going to have a delta S, which is going to be greater than 0. It's generating entropy. Now, we went on and said, well, what if, instead of just having this heat transfer process, we were to put a Carnot engine in here? So I'm going to put a heat engine in here that was reversible. It's a Carnot engine that is generating some work. So now I have a Q, and I'm going to call it QH, because it's going to be different than the amount that we were dumping down here, QL, different by an amount W. And what we saw here was that, well, we now know that QL is going to be less than QH. And so this number right over here, we've now got minus QH over TH plus QL over TL. But since this number has been reduced, we actually can end up having this being equal to 0. And so this cycle right over here actually generates no entropy. So we can go back and review and erase a little bit of that so you can see my equation here. Right over here, the entropy being generated is QL over TL. That's that second term minus QH over TH. So just kind of reverse the order here. And that's the entropy that's being generated. Now in terms of exergy, we talked about exergy, and that was just simply the entropy being the exergy destroyed was the entropy being generated, and then we multiplied it by this value T naught, which was some temperature in the environment, kind of what we call the dead state. And we could define then a second law, efficiency, which is the amount of exergy that we recovered over the amount that we actually put in. And from an exergy balance, this becomes 1 minus the exergy destroyed over the exergy that was expended. And so the exergy being expended is the amount of heat that we're putting in here, and then we also need to multiply that by 1 minus T naught over TH, recognizing that the best we could do would be a Carnot engine in there. So that right there would be the exergy that was being expended. All right. So that was just a little bit of review of exergy in the second law. And so just kind of, let me return here really quick. The key here at this point we're going to see is that where is the entropy being generated, because that is actually going to be what's destroying exergy. So here's our simple Rankine cycle where we just have points 1, 2, 3, and 4. So we have no feed water heater. And so where is entropy being generated? Well, the primary point that it's being generated is up here at the boiler where I'm adding heat. I've got QH, and that has to be at least at a temperature TH. And when we first come out of the pump, we're right down here, and so we're at some T low, and so we have a fairly large temperature difference that we're dumping heat into. And so we're generating a lot of entropy there. A little bit less as we move across here, but the point is right down here we're generating lots of entropy, and that's what we would like to go ahead and reduce. So that's what we did with the feed water heater. We're actually able to reduce it because with the feed water heater, here's my boiler. It's coming in at 0.4. Let me label a couple points. It's a good review. Here's our pump, our low pressure pump. That's 0.1 to 2. The middle stage of the turbine, that right over there, is 0.6. And what's coming out of the feed water heater was 0.3. And so 6 and 2 we're mixing to go ahead and form 3. 3 goes through the pump up to 0.4, and then we go up through the boiler at 0.5. And I'll just go ahead and label this for completeness there at 0.7. Now, here's my heat input going into the boiler. It's coming in at 4, and so the coldest it ever is at 4. So here's my TH value at a minimum there. And now the initial heat that's being added is starting off at this point. So I've preheated it. I've preheated it from this point to there. And so I'm clearly going to be generating less entropy as I go through this cycle. So what I have done is generated less entropy, which means I'm destroying less exergy. Now here's a good thing to consider though, is that you might think, but wait a minute, this is at some T high. I'll call it T high prime. It's a little bit different. It's warm. This is at some low temperature TL prime. It's something cold, and they're mixing, and so clearly there's heat being transferred from this fluid to that one. Isn't that also generating some entropy that I need to account for? Are we not accounting for this? And in fact, would maybe that be the same, because clearly there's some heat going on, and we're actually generating the same amount of entropy. So you give a minute to think about whether that is true. Is that an argument? Do I need to account for the heat transfer going on in that open feed water heater? Well, the answer to that is no. And let me go on and explain why. I'm going to erase some of the stuff that I drew on it. If I go ahead and just draw a box around my whole Rankine cycle like I've done right here, and I'm not going to look at the internal details, what I have is a steady state system. And this system is accepting some heat over here at QH and over here at QL. Now, if this is steady state, it means it's not changing in time. That means that its entropy cannot be increasing. So the entropy inside this system can't be going up, otherwise it wouldn't be steady state. It needs to have its entropy, and it has to be constant. So all I need to consider is the QH going in, and then clearly the QL, which is this point over here, and then also the condenser value. So I don't need to worry about the internals of what's going on for a steady state system. So although there's heat transfer going on inside it, it's not going to be an additional entropy generation. The entropy generation I only need to consider is on the outside of the box. And that's one of the kind of nice things about thermodynamics, is you can define these systems that come down to something that is a little bit easier to quantify, and you don't have to worry about the internal details. All right, so what we're going to do to kind of just put some quantifiable numbers on this exergy destruction is we're going to return to this problem we've done in the previous video. So here's our high pressure and our high temperature, and we have this open feed water heater, our condenser pressure. And I'm going to look at this problem both with and without an open feed water heater. So we'll look at a simple Rankine cycle between these conditions without the feed water heater, calculate the exergy being destroyed, and then we'll look at this example and look at the exergy being destroyed in this one, so we can compare the two and see that actually this example with the open feed water heater destroys less exergy. And then we're actually going to go and calculate the second law efficiency. So I'm going to go and do this in EES. And so first, let's go ahead and look at the simple Rankine cycle. So here I have is EES problem written up for the simple Rankine cycle. So up here at the top, I have my high and low pressure, 15 megapascals, condenser at 10 kPa, and my high temperature at 600 degrees, and then my condenser outlet is 0. And you can go through and review some of this as you want, and I'll post it on the website as well, but I've got an isentropic pump, an isentropic turbine, isobaric steps between the condenser and the boiler, and then I just calculate my enthalpy values, and then I can go ahead and find out my efficiency by calculating Q in and Q out. Now, if you remember also from a previous video, the mass flow rates are different if I have feed water heaters or not. And so when I compare these two, I need to look at extensive values. And so I'm going to make both of these systems generate 100 megawatts. So that's what power is here, 100 megawatts. And then that's going to go ahead and let me calculate my mass flow rate based on the net work produced on a per mass basis. Right. Now here's the key. I'm going to look at the exergy destruction term. So let's look down at this one here. X sub G, which is the exergy destroyed, I have is T naught, and then this whole term right over here that I've written is S gen. And so if you look closely, right, I have Q out, so that's the QL term, that's what's leaving the system, normalized by the temperature in my condenser, and that needs to be in absolute temperature, so I've got Q1 plus 273, minus Q in, that's the T high temperature, again normalized by the temperature, and I'm assuming the boiler is at T3, which is actually the lowest it could be. This is actually going to be the lowest amount of exergy that I'm actually destroying. So that's going to be X destroyed. My problem, I haven't actually anywhere specified T1, so I'm just reminding EES, having it solved for T1 as the saturation pressure in the condenser. and then I've got a value of T naught. I'm saying it's room temperature 298. So if we go ahead and solve this, and let's go ahead and look at our solution table here, the key thing I want to show is here's my exergy destroyed, and this is in extensive, so I'm destroying 44.429 megawatts. My power produces 100 megawatts, and I'm destroying 44 megawatts. So now let's go ahead and look at it with the feed water heater. Oops, there it was. Sorry about that. There we go. Okay, so here's the problem we did in the previous video with the feed water heater. So up at the top again, I have same conditions. The numbers are a little different in the feed water heater here. So now my boiler is at 0.5, the outlet to the boiler, inlet to the turbine. My constant pressure steps, condenser, and again I'm specifying that the feed water heater as a condenser outlet, or essentially not a condenser outlet, but it's a saturated liquid at 0. And again, this is sort of a review of stuff that we've seen in the previous video. So let's just go down to the bottom again, where again I'm going to calculate the exergy destroyed, and my equation is going to look more or less the exact same. So let's look here. We got exergy destroyed. I have T naught times the mass flow rate to make it extensive, and then Q out, which is this is QL leaving. I've got Q out normalized by the condenser pressure. Notice that I've weighted it by 1 minus Y because I've actually got a lower mass flow rate going through the condenser and the feed water heater by a factor of 1 minus Y. And then Q in again over the boiler temperature. That's similar to what we had before. So if I go ahead and solve this now and look at our values, what I see now is my exergy destroyed is just 10,000. And before, remember, it was about 44,000. Now again, they're both apples to apples comparison. They're both generating 100 megawatts, but I'm only destroying 10 megawatts with the feed water heater. So clearly, last time I destroyed 44,000 kilowatts, and now I'm only destroying 10,000 kilowatts. Okay. So let's go and calculate our second law efficiency. So let's come back to a slide here to do it. And so if I want to go ahead and calculate my second law efficiency, I'll do it up here. My second law efficiency for the system where I did not have a feed water heater, well, I was generating 100 megawatts or 100,000 kilowatts, and potentially I could go ahead and do 100, and then I need to add that I was destroying, which is 144,429. So there's actually the amount of exergy. The amount that I generated plus the amount that I destroyed is the amount that I could have gotten. Now, if I look at that, that's 0.69 or 69%. So it had a second law efficiency of 69%. If we look at the second law efficiency of that with the feed water heater, again, we were generating 100,000, and now, well, we destroyed only 10,000, so we had 110,000 that we could have gotten over 017, and that's 0.91. So our second law efficiency with the feed water heater is 91%. You realize we're getting pretty good. That single open feed water heater really increased my efficiency. Your second law efficiency, the highest that could ever be, would be 100%, and we're doing pretty good here by only destroying about 10% of what we put in with the feed water heater. Okay. So hopefully that example, the numeric example, kind of lets you see where entropy is being generated and how that is destroying exergy, and feed water heaters actually increase the efficiency.